Log on, tune in, find out. Another good idea from Cambridge.
A great pleasure to welcome Rolf Farnsteiner from Kiel, who will tell us about support spaces, Jordan types, and indecomposable modules.
Yeah, thank you very much. It's a great pleasure for me to be here at the Institute. Let me start out with a couple of remarks on the space of p-points. And for that, let me begin with the conventions that will be in force throughout this talk. So K will denote an algebraically closed field of positive characteristic. And the objects we'll be studying are finite group schemes. Defined over K. Such a group scheme comes along with its coordinate ring. K of G. And the representation theory of G that we'll be interested in is equivalent to the representation theory of the group algebra, or algebra of measures, which is the dual of the coordinate ring being a commutative Hopf algebra. K of G is a co-commutative Hopf algebra, and by general theory, every finite dimensional co-commutative Hopf algebra arises in this fashion. So the finite here refers to the fact that these algebras are finite dimensional. So if you're not familiar with this, of course, one example is K of G, the group algebra of a finite group. And if the characteristic were 0, then this would be the only example, and all algebras in question would be semi-simple by Maschke's theorem. So in positive characteristic, we have another standard example, the so-called restricted enveloping algebra. Of a so-called restricted Lie algebra G. This is a finite dimensional quotient of the ordinary enveloping algebra, and restricted really means that you have a p-map, so something like a p-power operator on G. So the Lie algebra of an algebraic group would always be a restricted Lie algebra. Okay, yes, the next, what are we going to study? So it's going to be mod G. So this is the category of finite dimensional G modules, which is the same as finite dimensional KG modules. And one tool to do this is to look at the even cohomology ring. So H of GK is the even cohomology ring of G. So this is a commutative algebra, and by the famous Friedlander-Suslin theorem, this is finitely generated. So that's really the starting point for the next notion. If you take a G module, you can look at its Yoneda algebra of self-extensions. And this Yoneda algebra of self-extensions canonically has the structure of a module over this finitely generated commutative algebra. And we're going to look at its annihilator and take the zero locus thereof. And what we're going to get is the cohomological support variety, which lives inside the maximal ideal spectrum of this finitely generated space. So Vg of M is the cohomological support variety. And it's a conical variety, which will be important later when we look at the associated projective varieties. Okay. Now these support varieties turn out to be important invariants, but they are, by nature of the definition, hard to compute. And so people started to look for alternatives, descriptions that would avoid the use of cohomology or the reference towards cohomology while retaining the homological features. And a very recent approach, well, now it's 4 years old, is due to Friedlander and Pevtsova, which unifies earlier approaches concerning finite groups, restricted Lie algebras, and infinitesimal groups. And that I would like to present next. So for that, we're going to use a standard algebra, which is the p-truncated polynomial ring. And we're going to study our module category by using algebra homomorphisms from AP into our group algebra. And along with such an algebra homomorphism, there is the pullback functor, which I will denote alpha star, which is an exact functor that assigns to every module its pullback along alpha. So here's the relevant definition. So in algebra homomorphism, alpha from AP into KG is called a p-point. Provided the following two conditions hold. So first of all, alpha is left flat, and second, there exists an abelian unipotent subgroup scheme U in G such that alpha factors through U, so such that the image of alpha sits inside KU. So before commenting on that, let me give you a little bit more notation. You can introduce an equivalence relation on P points. So you define two P points to be equivalent exactly when, for all M in mod G, the pullback along alpha is projective, which is the same as being free, if and only if the pullback along beta is projective. Yes, and so we then define point of G to be the set of P points, and the space of P points by definition is just a set of equivalence classes. So this definition may look somewhat contrived, so let me make a few comments. So first of all, P1 really means that the pullback functor takes projectives to projectives. If you think of the classical situation of cyclic shifted subgroups that John Carlson introduced, this is something you want there. It reflects the fact that support varieties of projective modules are trivial. The second condition is a little bit more subtle. Let me just make the following comment. it allows us to reduce many problems and questions that we may have involving p-points to questions concerning abelian unipotent subgroups. And an abelian, the group algebra of an abelian unipotent subgroup looks like the group algebra of an abelian p group. So that would be the specialization. So you get a truncated polynomial ring. And in this environment, this equivalence relation that I defined to you abstractly is actually amenable to computation, so we can handle things there. So maybe that's all I want to say about this for the moment. So what does this have to do then with the support varieties that I mentioned earlier? So given M and mod G, Friedlander and Pevtsova associated to M a certain space, a certain set rather to begin with. Namely, you look at those equivalence classes of p points such that alpha star of M is not projective. And you call this the p-support of M. So, and here is their first fundamental result. So there are two statements. So first of all, if you look at the collection of all these p-supports, so this is the set of closed sets of a Noetherian topology on P of G, and as a topological space, this is homeomorphic to the projectivized support variety of the trivium module. So there exists a homeomorphism C from the space of p points to the proj of the even cohomology ring, such that these closed sets are just taken to the support varieties that I introduced earlier. So one thing that you get from this is that the dimension of Pg of M is equal to the complexity of the module minus 1. You recall that the complexity of a module is the polynomial rate of growth of its minimal projective resolution. Okay. So what we've done so far, following their work, is really to show that certain approaches that were defined before in various other contexts, how they can be unified. But along with this new definition also comes a new point of view, which I would like to explain next, which before showed up sporadically in the literature, but wasn't really discussed systematically. Yes, so what I would like to talk about now is the the set of Jordan types. So instead of asking whether the pullback is projective or not, we can look at its isomorphism class. So if M is a G module and alpha is a P point, you can ask yourself, so what is alpha star of M? Well, by Kohl-Remark-Schmidt, it decomposes into indecomposables. But recall that the algebra is just a truncated polynomial ring, so that means it has exactly one indecomposable in each dimension ranging from 1 to P. So I get the direct sum I goes from 1 to P. I get certain multiplicities, and I get the unique I-dimensional indecomposable. So this is the I-dimensional indecomposable AP module. So what one gets there are these functions alpha I from mod G into the natural numbers, including 0. And so the isoclass, so class of alpha star of M, this is then the Jordan type of M relative to alpha, and JT of M, you get a certain finite set by letting alpha run through all these P points. So this is the set of Jordan types. So the study of Jordan types was initiated, say, 2 years ago by Friedlander, Pevtsova, and Suslin, and it's really only just emerging. So what I would like to tell you today are 3 aspects of this theorem, this theory, or this notion perhaps. One is that Jordan types provide finer invariance than support varieties do. The other one is that you can define new and interesting classes of modules looking at Jordan types. And the third part is the technical part, is that you can show indecomposability of certain classes of modules. So let me start out with the third part and give you just an illustration. So one class of modules that plays a crucial role in the theory of support varieties are the so-called Carlson modules. So if you take a non-zero cohomology class, then this, by general theory, corresponds to a homomorphism of the nth Heller translate into K. And you can then define L zeta to be the kernel of zeta hat, and that's the Carlson module. Of zeta. So in one reason you look at these modules is the following. So if n is even, then the variety associated to the Carlson module is just the zero locus of the element. Yeah? And that gives you then the possibility to study realizability of certain varieties. Yeah, let me just give you an example of what the P points of these Carlson modules look like. So for uniformity, I do this for P greater or equal to 3. I take zeta to be a non-zero cohomology class, and I exclude some degenerate case where L zeta happens to be 0. So first of all, if n is even and zeta is not nilpotent, then set of Jordan types of L zeta, well, you can either get a projective module, and then you just get a multiple of the unique projective of this algebra, which is the algebra itself, so the p-dimensional module. Or if the modules are non-projective, you get 1 plus p minus 1 plus some projective part. So if n is even and zeta is nilpotent, then the Jordan type of L zeta, the set of Jordan types is a singleton, so you just get what you had before. And perhaps, yeah, I should make a definition here. I talked about classes of modules. So M in mod G has constant Jordan type. Provided the space is a singleton, so these particular Carlson modules here are modules of constant Jordan type. So the third part is if n is odd, then things that depend a little bit more on cohomology. So the Jordan type of L zeta and alpha is either equal to 2 times p minus 1 plus something projective. This happens if alpha star of zeta is equal to 0, where alpha star now denotes the canonical map induced in cohomology between the cohomology ring of G and the cohomology ring of this algebra AP. And it's p minus 2 plus projective otherwise. Okay, so in this case, one can compute these Jordan types, and this then allows you to prove the following. So under these conditions, that we have a non-zero class such that L zeta is not equal to 0 and p is greater or equal than 3. You have that if n is even, zeta is nilpotent. There is a more technical result for the non-nilpotent case, which I won't write down. If n is even, then L zeta is indecomposable. And if n is odd and you have enough large unipotent subgroups, so the space P of G can be written as the union of all abelian unipotent subgroups of complexity greater or equal than 2, meaning that you have at least n equal 2. Here the number of variables is at least 2. Then L zeta is indecomposable. And in fact, if you are dealing with a finite group, so a reduced group scheme, then the situation is better because the case where this is violated, you can apply equivalence dimension theorem and can also show that indecomposability holds. Yeah. Maybe I should say a word about the proof. Let's look at this case here. So we have a module here of constant Jordan type. Assume we have a decomposition, and the theory tells you that each summand also has to have constant Jordan type. And you see there's not much space here for these submodules. You can never have a projective submodules because the L-zetas are projective free. So you can only have modules of constant Jordan type 1 plus projective or p minus 1 plus projective, and those are the so-called endotrivial modules. And there you just have more information and to rule out that you don't have two summands in there. Okay, so I started talking about indecomposable modules. So indecomposable modules are studied by means of Algebraic theory. So we get to invariance. So invariance of Algebraic components. So being a finite dimensional Hopf algebra, K of G is self-injective. It's even a Frobenius algebra. And in this situation, one associates to the module category the so-called stable Auslanderite quiver. So this is a directed graph which has the following ingredients. So the vertices are the non-projective, indecomposable G modules. And you have arrows between two such isoclasses. So here I should have written isoclasses of these modules. You have an arrow between two such isoclasses when there is a so-called irreducible morphism. So as a first approximation, you can think of this as a morphism that doesn't factor properly through another indecomposable. So these are really then neighbors that are connected by arrows. And as a third ingredient, the so-called Ausländerreiten translation, which is an automorphism of the quiver, tall sub G, and you're sending a module to the composite of the square of the Heller operator with the functor nu G, and nu G is the so-called Nakayama functor of the algebra. So if you do finite groups, you won't see it because in that case you have a symmetric algebra, and then the Nakayama functor is always the identity. Okay. So given the fact that for most algebras you will not be able to classify indecomposable modules because they are wild, one is interested in the structure of this quiver. It's an important invariant of the Morita equivalence class of such an algebra. And yes, so the starting point is to notice that these are the data of what's called a stable translation quiver, and the connected components can be described by work of Christine Riedmann as follows. So you take a component in gamma S of G, then you can attach to this component a directed tree, and you go further then to forget about the orientation and call this the tree class. And it turns out that you can recover the component from certain data along with this tree class. And let me just give you one example of a result of a type of component that will show up rather often. So this is the quiver ZA infinity. So the underlying tree is the infinite Duncan diagram of type A. So you just start at some point and move off into some direction. And the points here are represent indecomposable modules. And the Außenderreiten translation is just the shift here in one direction. So, and you can find many directed trees of type A infinity inside here. You can move along this line, but and then take copies of it. But you can also move along this line and get another orientation, or you can zigzag through and get any orientation you want. So this is why it's the undirected tree that gives you the isomorphism class of the quiver. Now, you can do more. I mean, you can start identifying ends here, and then you get a certain tube of a certain width when you have so-called periodic modules around. We will see this in a moment. And you can identify the position of a module inside this quiver by the so-called quasi-length, which is the distance towards the end here. So here are all modules of quasi-length 1, which is the quasi-simple modules. Then you move up here, quasi-length 2, quasi-length 3, and so forth. Yeah. Okay. So this is, and you can do this with other trees as well. Yes. Okay. So what does this have to do with what I said before? Now, first of all, support spaces give a certain invariant. So one observation one makes is that you take two modules belonging to the same component, then the P support doesn't change, which means that actually these supports are invariants of components rather than modules. And these components, as we will see, actually tell you a great deal of the possible tree classes that can occur. Rieman's theorem is really very abstract work where you forget that you're dealing with modules. So if you remember that you're dealing with modules and you have length of a modules and certain invariants like the one here, you can show the following. So this tree class T theta is either a finite Duncan diagram, an infinite Duncan diagram, so one example we have seen, one other one we will see in a moment, or a Euclidean diagram. And another observation is the following. If the dimension gets too large, then such a component will automatically be of the type that I gave you before. So in many cases, this is sort of the generic type that you have, and you can deal with quasi-lengths. Okay, and so yes, perhaps I should give you another example where this can be worked out. So this example may look somewhat contrived in terms of the choice of groups that I'm going to confront you with. Namely, what we're going to do is we're studying the algebraic group SL2 and take inside SL2 the standard maximal torus of diagonal matrices, and our group G then will be a product of the first Frobenius kernel of SL2 with the rth Frobenius kernel for any R of this standard maximal torus. So these groups naturally come up when you classify infinitesimal groups of tame representation types. So this is why you start looking at these things. So the module category of SL1 to R is, roughly speaking, the module category of the enveloping algebra of SL2 that I mentioned earlier, but then each module endowed with a grading by the group Z mod P to the R. So this is how you can think of this module category. Yeah, it's sort of a covering. Okay, so let's take this group and let's take a component. So in this case, the P support is one-dimensional. So these components, the supports of these components can only have dimension 1 or 0. So if the dimension of the component is 1, which really means that you get the full support space here, then I don't want to write down the component because I would have to introduce some more terminology. Let me just tell you what the tree class is. It's either if R is greater than 1, a double infinite, or if it's if R is equal to 1, then you just get the Lincoln diagram of affine SL2. And yes, and there is a number S theta between 1 and P minus 1 such that the Jordan type, the set of Jordan types, is just S theta plus something projective. And so the second possibility is that the dimension here is 0. Then you remember that means that the modules all have complexity 1, which means that they are periodic. So then theta is either one of those tubes of width 1, or you get a tube of which of width P to the R minus 1, which, by the way, is the maximal width allowed according to the Friedlander-Suslin theorem, because of the way the cohomology ring is generated. Yeah? And so then we have JT of M. This is either you get something projective, or you get, okay. So there is a number I theta, which I have to define in a moment, plus P minus I theta plus something projective for all M in theta. So in I theta is between 1 and P minus 1 over 2. Yes, so what I would like to explain for the rest of the lecture is some results that explain these phenomena a little bit, but let's look at this for the moment. So first of all, these modules here are all of constant Jordan type, and it turns out they have the same support space, but if you look at the set of Jordan types, it nicely separates the components. You really have exactly P minus 1 of them. Here you see that you tend to have a problem when the dimension goes down, because I cannot separate, by looking at Jordan types, the homogeneous tubes, those of width 1, from separate those from those of width P to the R minus 1. For that, you need actually the theory of so-called GRT modules that tell you a little bit more about this situation. So this the Jordan types won't do for you. Okay. Okay, so how can we explain this? Here I need one more notion. So let M be non-projective indecomposable. And then there's a certain short exact sequence starting in tar G of M and ending in M. This is the so-called almost split sequence. Terminating in in M. So this these almost split sequences are related to the structure of the Alexander-Ruyton component of M, namely the predecessors of M or the successors of tar G of M are just the non-projective indecomposable summands of EM. So when we go back to this example here, so you have an almost split sequence starting here. You go into the direct summand of these two modules, and here is the point where you terminate. And you see the starting point here is just the Alexander-Ruyton translate of the endpoint. So here you always have two non-projective indecomposable summands. And by the way, having projective indecomposable summands is a rather rare occasion. When you have a quasi-simple module here, then the middle term is usually indecomposable. Yeah. Okay. So why did I write this down? So let M be non-projective indecomposable. No, let theta be a component. Let theta be a component. And alpha be a p point. Then theta is said to be alpha split if alpha star of EM, so I can apply the exact functor to this sequence. This one here is non-split, but I may get something split. If this is split for all M in theta, and theta is called locally split, if theta is alpha split for all p points alpha that you have. Okay, so here is the proposition that relates this to our p support. So you have a component theta and p point alpha. So the first statement tells you that not being alpha split is actually a rare occasion. So if theta is not alpha split, then the p support of the component is just a singleton given by alpha. And if you remember the classification of these tree classes I had, this has an impact then on the tree classes that can occur. So in either theta is finite, meaning that its tree class is a finite Dynkin diagram, or theta is one of these tubes that we looked at before. Okay, so immediate consequence is if the dimension of the support is greater than or equal to 1, then theta is locally split. Yes, and why would you be interested in having locally split components? So if theta is alpha split, then these functions alpha I that you get by looking at the coefficients of the decomposition of a pullback of a module from theta into the natural numbers including 0, this function is tau g invariant, meaning if you precompose it with tau g, you get alpha I back, and additive as long as I ranges between 1 and p minus 1. So additivity refers to being additive on these almost split sequences. Okay, so this means that we have to look at two cases, those where a component is split, locally split, and the others where it's not. So to do that, let me introduce a set of those p points where theta is alpha split. So the following theorem tells you that what's going on in terms of developments of Jordan types is sometimes determined at a very few places. So let theta be infinite. Be an infinite component. So then there exists a tau invariant, tau g invariant additive function f theta, so from theta into the natural numbers, but now excluding 0, and a function, say, d theta from this set here, such that if you take alpha I of m for some m in theta and for some I between 1 and p minus 1, then this is just di theta of alpha times f theta of m for all alpha in this set. Okay, so let's look at our example. Perhaps make a following remark. So these, depending on the type of the tree class of this component, these functions are well understood. So if t theta bar is a infinity, then f theta of m is just the quasi-length of m for all m, and if t theta bar is a double infinite or a1 to tilde, then this function f theta is identical to 1. Okay, so yes, so what happens in our first example here? Here the dimension is 1, so the component is locally split, which means that the subsets there coincides with the whole set, and this function f theta is constant. So it really suffices to evaluate things on one particular module, and it turns out that these components all contain a simple module, and for the simple module you can find the Jordan type, and this is why things develop in this way in this particular example. So let me digress for a moment and give you some consequence. I talked about invariance. So suppose that theta is locally split. Then you see here that the number of elements in the Jordan sets doesn't change. So then actually what you get is that the number of Jordan types is just the image of this function d theta for all m in theta. So here we have a new invariant of an AR component. And this allows us to retrieve a recent theorem by Carlson, Friedlander, and Pevtsova, who proved the following. So if theta is a component, locally split or not, containing a module of constant Jordan type, then all m and theta have constant Jordan type. Okay, so you get this immediately if theta is locally split, and if theta is not locally split, this proposition here tells you that in fact the whole space, if you have constant Jordan type, then the p support of a modulus, the whole support space just has one point, and so you're in a very particular situation that we can also verify this. Yeah. Okay, so what I'd like to discuss in the end is the other case that you have in this example. And unfortunately there things are not that clear yet. So now assume that theta is not locally split. And assume it's infinite. Then recall that this means that theta is one of these tubes. So we have the quasi-length of modules belonging to this tube. So in here the situation in certain cases is governed by the following. You have a certain matrix and this is simply the Cartan matrix of AP minus 1 of the Lincoln diagram. So let theta be an infinite component. Alpha a p point such that first of all, theta is not alpha split. And B, if n in theta is such that alpha star of En does not split, so things go wrong, then the quasi-length of n is 1. I'll comment on that condition later on. So then you can find numbers n1 through np minus 1 non-zero natural numbers, and m and theta of quasi-length 1, which one you take doesn't matter, such that if you want to compute for a module x in theta alpha I of x, you take alpha I of m minus the sum j goes from 1 to p minus 1 aij nj times the quasi-length of x, and then you have this correction term here again. And this is again true for all x. I already stated that, and I between 1 and p minus 1. So the problem, of course, with applying this result is, does condition B ever happen? And here are some instances. So B can be verified in the following instances. So first of all, if theta contains a module having a one-dimensional simple module in its top or socle. So for some module, of course, this will always happen. In this case, we have that the ni actually either 0 or 1. So when is this automatically guaranteed? If G is a Frobenius kernel of a smooth algebraic, solvable algebraic group. So then the Lie-Kolchin theorem guarantees you that all simple modules are one-dimensional, and then you just have ni is even delta ij for some j depending on the component theta you started out with. In the setting of finite groups, so G is a finite group, and theta contains a module with a cyclic vertex. So then condition B also holds. Yes, and finally, this situation here where you have our favorite example and a component whose variety has dimension 0, then you first have this situation here. And well, this SL2 situation is nice because translation functors allow you to move around. And a lot of the modules here have a so-called G1T structure, and you have an Auslender-Reiten theory there. And so translation functors allow you to shift this information around. And this is why you get things here. And the algebra just works out the way that everything here is constant, equal to 0 or 1. Thank you very much.